The research paper introduces a novel storage method called stochastic emergent storage, SES, which leverages natural randomness to construct an emergent representation of the desired memory. This approach is based on the concept of emergent archetypes, where a training set of imperfect examples, prototypes, is used to instantiate an archetype in an Hopfield-like network through emergent processes. The study demonstrates this non-Hebbian paradigm in the photonic domain by utilizing random transmission matrices, which govern light scattering in a white paint turbid medium, as prototypes. The SES-BASED optical hardware, the disordered classifier, is capable of efficiently performing pattern storage and subsequent pattern retrieval. It can simultaneously compare an input pattern with thousands of stored elements, and it enables a two-layer architecture, providing categorical, deep classification, which allows for more complex tasks. The idea stems from the fact that intensity scattered by a disordered medium into a mode nu resulting from an input pattern phi may be written as I nu phi equals phi v nu phi, with the scattering process driven by the matrix v nu equals xn circled times xn, generated from the tensorial product of the transmission matrix ρ, transmission vector, xn with its conjugate transpose xn. The authors propose a novel method to store arbitrary patterns in naturally occurring scattering media, exploiting the fact that a scattering process generates billions of output modes, each with a unique and random embedded memory pattern. They introduce a photonic linear combination of optical synaptic matrices to generate an arbitrary optical synaptic matrix, realizing an optical equivalent of the Heb's rule, called stochastic Heb's storage, SHS. In SHS, a synaptic optical matrix Jm, lambda t is generated by a linear combination of a set of random optical synaptic matrices resulting from uncontrolled scattering. The matrix Jm, lambda t is connected to the intensities of the modes pertaining to the set M with equation 5. The values for coefficients lane are obtained by a Monte Carlo algorithm, minimizing the difference between the target matrix and Jm, lambda t. The authors demonstrate the performance of SHS in Figure 2, showing that SHS is Bézier-Hungry, requiring a large number of random optical synaptic matrices to successfully construct a memory element. However, they also propose an alternative approach, called stochastic emergent storage, SES, which greatly improves the performance. In SES, a set M of optical synaptic matrices is selected based on the similarity of their intrinsic memories to the target pattern phi. The attenuation coefficients lambda are found by minimizing the distance between the archetype pattern to be stored phi and the matrix first eigenvector SEIG, Jm, lambda phi. The transformed intensity in SES reads Im lambda phi equals phi Jm lambda phi equals mn array summation nu lane I nu phi. The authors demonstrate the potential of SES in Figure 3, showing that SES greatly outperforms the random selection approach, with an order of magnitude improvement in storage error probability and 3 to 4 orders of magnitude improvement in classification error. They also demonstrate the emergent learning process, showing that the system can work as a content addressable memory, simultaneously comparing an input with all memories stored. The research paper introduces the stochastic emergent storage, SES, paradigm, which enables classification with a significantly smaller number of sensors, pixels, modes compared to the elements composing the pattern. This approach leverages the Hebbian structure of the synaptic matrix and explores the potential of a stochastic innate network, where predetermined random synaptic structures are combined to generate memory elements in an emergent manner. The SES paradigm contributes to the ongoing challenge of understanding the biological memory formation process and offers a fresh perspective to the problem. In the context of wavefront shaping experiments, light from a coherent source is controlled by a spatial light modulator and transmitted through a disordered medium. The field transmitted at a specific mode nu is described as a sum of fields from controlled segments, each transformed by a transmission matrix element. The experiment simplifies the configuration by considering only 2 active segments with a +1 phase configuration. The intensity is written as the modulus square of the field, recognizing that the modulus of the field is a Gaussianly distributed complex number. Stochastic Hebs storage protocols introduce tailored attenuation coefficients lambda to design an arbitrary optical operator, enabling the storage of user-designed patterns. The storage error probability and classification error probability are measures of the storage and classification process's effectiveness, respectively. These probabilities are calculated based on the number of error pixels in the stored pattern image and the number of wrongly identified patterns, respectively. The lower these probabilities, the better the storage and classification processes. The stochastic emergent storage protocol leverages the optical coupling matrix V-nu to host random patterns for memory applications. A multi-step strategy involves measuring transmission matrices using the complete couplings mapping method, saving them in a computer memory, and finding the first eigenvector for each matrix. The target pattern phi and the number m of modes are designed by the user. The modes are then similarity decimated to select the m modes with the highest similarity to the target pattern. The attenuation coefficients lambda are optimized using a Monte Carlo algorithm, aiming to minimize the eigenvector similarity function f. Lambda, phi, m. The experimental setup includes a single-mode laser, a digital micromirror device, and a diffusive medium to measure the optical synaptic matrices V-nu. The complete couplings mapping method is used to reconstruct the full synaptic matrix, requiring 3 intensity measurements per element. The data are organized into a large matrix, limited by the random access memory size of the computing workstation.